Hey everyone! In this lesson I'm going to show you another way to work with bits. We already learned how to work with bits inside variables, but it's not very convenient. We have to use bitwise operators and write code that isn't exactly clean or easy to read. Let me remind you what that looks like in the following example. Once again, I'll use a handy alias for working with 1 byte. We have a variable that controls the fan settings. The rightmost bit means the fan is on, the second bit from the right controls rotation, and the third bit controls the speed. If we want to turn on one or more bits, we write code like this. If we want to turn a bit off, we write code like this. If we want to check whether a bit is on or off, we write code like this. That's a lot of bitwise operators. It would be much nicer if each bit has its own name and we could use normal, easy-to-read operators like this. We'd access the fan settings variable, then access each bit separately and assign it a clear value. And that's actually possible. For that, we use bit fields. A bit field is a variable that's a member of a struct or class, and its size in bits is defined by the programmer. But first, let me explain something important. You can create an empty struct. If we create an object of that struct and check its size using sizeOf, we won't see 0, we'll see 1. The reason is that even structs without any fields or variables must occupy their own space in memory. Otherwise, they would all end up at the same memory address, which would cause problems when distinguishing between different objects. So, if a struct has no fields, its size will be 1 byte, because that's the smallest unit of memory that has its own address. Now let's go back to bit fields. I created a struct. Inside it, I used the syntax for declaring a bit field. You write the type, then the variable name, then a colon, and then the number of bits that variable should take. The first question that comes up is, why do we even need to specify a type if we're already telling it how many bits to use? Let me remind you that we have types like int and float. They both take up 4 bytes. But int stores whole numbers using its own bit rules, while float stores fractional numbers using a completely different bit layout. So when you specify the type, you're basically telling the compiler how to interpret that chunk of bits. Let's look at an example. We have a regular variable. It takes 4 bytes. Then we have a bit field that takes 2 bits. I used unsigned int to emphasize that we can store an unsigned integer inside those 2 bits. 2 bits can only hold the numbers 0, 1, 2, and 3. If we create an object of this struct, how much memory will it take? It can take 4 bytes and 2 bits because the smallest addressable unit in memory is a byte. So maybe the object will take 5 bytes? No, it will take 8 bytes. This is because of alignment, which I talked about in the lesson on structs. The largest type here is int, which takes 4 bytes. So everything smaller gets aligned in 4 byte chunks. That means 4 bytes are allocated for the first variable and another 4 bytes are allocated for the second variable, even though it only needs 2 bytes. Alright, now let's create a struct that only has that bit field. How much space will an object of that struct take? I said earlier that any struct must take at least 1 byte. So maybe this one will take just 1 byte? No, it will take 4 bytes. Because we declared the type as unsigned int, which takes 4 bytes. I know, this sounds confusing. I just told you that we specify the type in a bit field to explain how to interpret the number of bits we assigned. But now it looks like variable b doesn't take 2 bits, and not even 1 byte, but a full 4 bytes. So did I lie? I didn't exactly lie, I just didn't explain the whole thing. The type specified to the left of the bit field's name is the type of what's called the allocation unit. A bit field doesn't exist on its own, it lives inside this allocation unit. The size of that allocation unit is determined by the field's base type. In our case, the base type is unsigned int. It takes 4 bytes. That's why the struct will take at least 4 bytes. So what actually happens in memory? When the object is created, 4 bytes are allocated. Imagine each x as a single bit. There are 32 of them. The bit field only uses the first 2 bits of that memory. To understand this better, let's look at another example. I created a struct that has 5-bit fields. Together, they take up 27 bits. If we create an object of this struct, it will still take 32 bits. That's 4 bytes. But this time, visually, it would look like this. The first 2 bits are assigned to variable b, the next 3 bits go to variable c, and so on. The last 5 bits remain unused. Here's a simple way to think about it. A bit field is just a name for a specific number of bits in memory. We specified unsigned int as the type, which means memory is allocated in 32-bit chunks. We gave the first 2 bits the name b, the next 3 bits got the name c, and so on. So how do we actually use these bit fields? The same way we use regular variables. First, let's create a struct that's actually useful and familiar, a fan. We're no longer calling it fan settings because the object itself is the fan, and its settings live inside it. Inside the struct, I define another type, an enumeration called speed mode. Why and how does it work? First, you can define structs and enumerations inside other structs. When you do that, their scope is limited to that struct. That means speed mode is only visible inside the struct. If we want to use it from the outside, we have to write the struct name first, then use the scope resolution operator, and then the enumeration name. Why didn't I move the enumeration outside the struct? Because the concept of speed mode by itself doesn't clearly say what it belongs to. We could rename it to something like fan speed mode, but first, that makes the name longer, and second, keeping the enum inside the struct conceptually reinforces the connection between the enum and the struct. In this case, the speed mode is directly tied to the fan. Also notice that I explicitly specified the underlying type of the enum as byte, so enum variables take up 1 byte. Otherwise, the default would be int, and here we're trying to save memory. And just to be clear, defining types inside a struct doesn't add any extra memory to the struct's objects. Next, I create 3 bit fields. The first one takes just 1 bit. That means it can only hold 0 or 1. 0 means the fan is off, 1 means it's on. The bool type is perfect for this, since it normally takes 1 byte. The same idea applies to the is-turning bit field. Then we have the speed mode bit field, which takes 2 bits. 0 means no speed, 1 means low speed, 2 means medium speed, and 3 means high speed. Why did I use the speed mode type instead of something like bool or byte? Because this way we can assign meaningful named values instead of raw numbers like 0, 1, 2, and 3. You'll see that in action in a moment. Now, the next question. How much memory will an object of this struct take? First, we determine the largest data type in the struct. Bool takes 1 byte and speed mode also takes 1 byte, so alignment will happen on a 1 byte boundary, meaning the minimum size of the struct is 1 byte. How many bits are we actually using? 4, because 1 plus 1 plus 2 equals 4. So the struct object will take 1 byte and we'll use only 4 bits of it. The other 4 bits will remain unused. Now let's actually use it. I create a variable called fan. Then I assign values to each field and look how much cleaner this is. No bitwise operators. If we had used byte instead of the enum type, we'd have to write magic numbers here or define separate constants for them, and we could even accidentally assign invalid values like 100. But with an enum, we get a strict limitation that says assign only enumerators, nothing else. Now, look how easy it is to analyze these bit fields, just like regular variables. If the fan is on, then we print a message, and with the ternary operator, we also check whether it's spinning. Then, inside a switch statement, we check the fan speed mode and print a message. Notice that inside the switch you can use the using enum keyword followed by the enum name. Thanks to that, inside the specific switch, you don't have to write something like fan, speed mode, some value every time. You can just write the enumerator names directly, and the compiler will understand you. Now let's move on to the next example, where we'll go over several important details about working with bit fields. First, the type of a bit field must be something that can be interpreted as an integer type. For example, bool, all integral types, all character types, and also enum types, because the underlying type of an enum is an integer type as well. Second, if you assign a value to a bit field that requires more bits than the field actually has, the value will be truncated. Only as many bits as the field size allows will be stored. In my example, we create a bit field that has only 3 bits. Then I create an object of the struct and assign the value 100 to that field. The number 100 in binary looks like this. It uses 7 bits. Only the first 3 bits will be stored in the bit field, which is 100. That's 4 in decimal. Third, sometimes you don't want bit fields to be packed one after another inside the same allocation unit. For example, when you need an exact match to a hardware register, or you want to separate groups of bits, or you need forced alignment. In that case, you can declare an unnamed bit field with a size of 0. Here's how it works. We have the first bit field of type unsigned, short for unsigned int. That means its allocation unit is 4 bytes. The first 3 bits of those 4 bytes are used for that field. Now imagine you want the next bit field to be placed not in those same 4 bytes, but in the next 4 bytes, meaning you want to start a new allocation unit. Right after the first bit field, you write a declaration with no name and a size of 0. That basically tells the compiler, stop packing into the current allocation unit. So the next bit field, which takes 2 bits, will be placed in the new allocation unit. As a result, an object of that struct will now take 8 bytes instead of 4. Fourth, you cannot take the address of a bit field. Fifth, bit fields can be initialized directly inside the struct definition, like I did in this example. You can use any valid initialization syntax. Sixth, the number of bits for a bit field must be less than or equal to the number of bits of its underlying type. For example, if the type is bool, then the number of bits must be less than or equal to 8. Otherwise, expect trouble. And seventh, the number of bits cannot be negative or fractional. And that's basically it. Bit fields are a really convenient tool when working with bits, but they're not always the right choice. You should use bit fields when you have a struct with several flags or small numbers that logically belong to the same object. In that case, the code looks clean. You just specify how many bits each field takes and use them like normal variables. It's a good fit when you don't need strict control over the exact memory layout and you're not planning to send the raw data over the network or write it to a file as is. On the other hand, working directly with bits using bitwise operators is better when you need precise control over which bits go where. For example, when data has to be sent over a network, saved to a binary file, or when your program needs to behave identically across different platforms. This approach is a bit less convenient, but more reliable and predictable. That's because bit fields are not fully standardized. For example, the standard doesn't guarantee the direction in which bits are packed, left to right or right to left. That means the same code can result in different memory layouts on different compilers or architectures. Also, if you have several bit fields in a row, the standard doesn't guarantee that they will always appear in the same order in memory or exactly how they will be packed inside a byte. And that's it for this lesson. Thanks for watching. If you enjoyed this video, you can support me by liking it, leaving a comment, subscribing to the channel if you haven't already, donating through the link in the description, or using the YouTube Thanks feature. If you want to reinforce what you learned in this lesson, you can become a channel member and get access to all the practice lessons. Just find the practice video with the same number and work through the tasks together with me. See you in the next lesson.